Hello, I'm Mark Hornick with Machine Learning Product Management at Oracle. Welcome to this session, Oracle Machine Learning, What's New and What's Next. The converged Oracle database and autonomous database continue to grow as platforms for data science and machine learning. In this session, you'll learn about the latest enhancements and upcoming new features in Oracle Machine Learning that makes the database a powerful engine for solving data-driven business problems. This is Oracle's safe harbor statement, since I'll be discussing our product roadmap. By the end of this presentation, you should be able to answer three important questions. What is Oracle Machine Learning and its latest features? What's next on the roadmap? And how can I get started? Let's start off with the broader Oracle Machine Learning product family. Oracle Machine Learning provides interfaces for machine learning in the database for three popular data science languages, SQL, R, and Python. OML for SQL provides a SQL interface to the in-database parallelized algorithms, which keeps data under database control, eliminating the need to extract data to separate machine learning engines. OML for Py and OML for R are Python and R language interfaces, and these allow you to manipulate database tables and views using familiar functions and syntax, while also exposing the in-database algorithms using native APIs, among other features. Now, for interaction with autonomous database, we provide OML notebooks with SQL, PL/SQL, Python, R, and Markdown interpreters. The same notebook can contain paragraphs using each language, allowing users to choose the most effective language for a given task. Notebooks can also be scheduled to run automatically. Now, Oracle Data Miner is a SQL developer extension that enables users to create, schedule, and deploy analytical workflows through a drag-and-drop user interface. OML for Spark provides machine learning in the big data environment, such as Big Data Service. And Oracle Machine Learning AutoML UI is a no-code user interface that automates the model building selection and deployment process. Lastly, Oracle Machine Learning Services is a RESTful service for model deployment and management, along with cognitive text analytics. I'll comment on a few of these in more detail before we begin with new features. First, let's take a closer look at OML for SQL. The parallelized algorithms keep data under database control. There's no need to extract data to separate machine learning engines. This is the core of the "bring the algorithms to the data" tagline. Extracting data can be time-consuming and introduces issues of data security and storage, as well as the possibility of working with stale data. The in-database machine learning algorithms are fast and scalable, enable batch and real-time scoring, and provide explanatory prediction details, so you can understand why an individual prediction is made. In-database machine learning models are first-class database objects. You can control access by granting and revoking permissions, audit user actions, and export and import machine learning models across databases. OML for SQL supports the R and Python interfaces to the in-database algorithms, which reap the same benefits. But let's look at those more closely. OML empowers data scientists with open source Python and R by leveraging the database as a high-performance computing environment. The functionality across these interfaces is characterized in three areas. Using proxy objects, the transparency layer allows users to operate on database data using familiar Python and R syntax, overloading select functions that construct SQL for in-database processing. The in-database algorithms are exposed through natural Python and R interfaces, affording users the same scalability, performance, and features. And through embedded execution, user-defined functions can be invoked on database environment spawned and controlled Python and R engines. Embedded execution enables data parallel and task parallel processing. For example, an open source model can be scaled to large volumes of data for making predictions by requesting that multiple engines be spawned to process chunks of data in parallel. OML provides the supporting infrastructure to simplify and automate this process. In addition, OML for Pi supports AutoML, which includes automated algorithm and feature selection and model tuning. It also supports model explainability to provide algorithm-agnostic ranking of features impacting model predictions. To give you a clearer idea of what we mean by the transparency layer, we use proxy objects that reference tables and views, along with overloaded functions to take advantage of database column indexes, query optimization, parallelism, and even table-level partitioning. This can greatly improve performance and scalability on database table operations, since the data is not brought to the client engine. There are several ways to get proxy objects. We can create a table from a Python or R data frame, specifying the table name we wish to use. If the table already exists in the database, we can use the sync function and specify the table name to access. Each of these results in a proxy object that we can then use to invoke familiar Python functions like shape and describe, and R functions like dim, head, and summary, along with dplyr functionality. These overloaded functions, in effect, translate requests to SQL for in-database processing. So whether our table has 150 rows, like Iris, or 150 million rows, there's no overhead for pulling data to the client, and no worries about data fitting in memory. All computation occurs in the database. Building upon OML for Pi's AutoML, the AutoML UI is a no-code user interface supporting automated machine learning for both data scientist productivity and non-expert user access to in-database algorithms. Like AutoML in OML for Pi, the UI accelerates machine learning projects by giving feedback on dataset suitability for producing useful models, alleviating much of the repetition of the machine learning process. The AutoML UI automates model building with minimal user input. Just specify the data and the target in what's called an experiment, and the tool does the rest. Users can adjust some settings, such as the number of top models to select, the model selection metric, and even specific algorithms. With a single click, users can generate editable starter notebooks, and these notebooks contain code for data selection, building the selected model, including the settings used to produce that model, along with scoring and evaluation code. This is all in Python using OML for Pi. You can build on this generated notebook to apply your own domain expertise to augment the solution. Now, in addition, you can deploy models to OML services from the AutoML UI as REST endpoints in just a few clicks. It's important to understand where the various OML components and interfaces are available. Now, OML for SQL is available across database versions and supported operating systems because it's included in the kernel of the database software and can be used from any IDE that supports SQL access to the database. OML for Pi is pre-installed on ADB Shared and can be explicitly installed on 19C and 21C database instances on Linux. OML for R is also pre-installed on ADB Shared and can be installed on database instances as well. OML notebooks, the AutoML UI, and OML services are available on ADB Shared. And Oracle Data Miner can access both Oracle Database and Autonomous Database instances. Note that OML components are included with your database licenses or Autonomous Database instances. Oracle Machine Learning, in combination with the database, supports the broader machine learning lifecycle. The database provides the core scalable support for data acquisition and scalable transformations, profiling, and feature engineering. OML extends this with over 30 in-database machine learning algorithms and AutoML. OML supports model and individual prediction explainability and multiple deployment options, among other features. So now let's look at what's new in OML. Since the beginning of last year, we released OML for Pi, OML services, and the AutoML UI for Autonomous Database. We also released OML for Pi for Oracle Database on premises. In response to customer feedback, we enabled features of Oracle Data Miner on Autonomous Database, giving users access to the no-code drag-and-drop user interface through SQL Developer. We made several enhancements to OML notebooks, including bringing the notebook repository into the ADB instance, which enables cross-region data guard support. So let's look at a few of these new features in more detail. We'll start with OML for R. On Autonomous Database, we most recently released OML for R 2.0, which further expands ADB as a platform for data science and machine learning. Along with R 405, users can take advantage of recent R engine performance enhancements. We've added APIs for several in-database algorithms: XGBoost, exponential smoothing, neural network, and random forest. And these afford users the same scalability as the other in-database algorithms. To facilitate deploying R-based solutions with applications and dashboards, OML for R on ADB has REST and SQL APIs for embedded R execution. This allows users to deploy user-defined R functions from SQL queries and REST endpoints using a system-provided container architecture. The second new feature I'll highlight is the SQL API for OML for Pi embedded execution on Autonomous Database, which in many respects also applies to the corresponding OML for R interface we just talked about. Recall that embedded Python execution enables users to invoke user-defined Python functions in database-spawned and controlled Python engines, even with system-supported data parallelism. On Autonomous Database, users already had Python and REST APIs. The addition of the SQL API makes it easier for applications and dashboards to uptake Python results, since structured data frame and image results can be easily returned through a SQL row set or materialized as tables. Let's take a quick look at an example. Our goal here is simply to build a machine learning model using Python and store that model in the database, then invoke this from SQL. On the left, wrapped in a PL/SQL block, we have a user-defined Python function that builds a linear model from scikit-learn, saves this model in the database, and returns the model type. We're storing this function in the database Python script repository with the name myLinearRegressionModel. On the right, we show invoking this Python function from SQL using the PyQTableOfVal table function. We pass in the name of our table, Iris, and arguments to our user-defined function. There are several output format options, but here we specify XML. Users can also specify JSON, PNG images, or structured table output. And finally, we pass the name of the function we just stored in the script repository. Running this select statement results in a Python engine being automatically spawned, the function loaded, and the table data loaded as a pandas data frame. When it's finished, you have a native Python model stored in the database, ready to be used by another Python user, or an embedded execution invocation, such as row_eval, which provides system-supported data parallelism. As I mentioned earlier, OML Services provides a REST interface for model management and deployment. It supports real-time scoring of classification, regression, and clustering models, where users pay only for the compute consumed by the actual scores. The VM infrastructure is provided as part of Autonomous Database. OML Services supports both in-database and third-party ONNX format models. In this enhancement, we introduce support for ONNX format clustering models. ONNX format models, you may know, allow users to build machine learning models in separate environments and use packages like TensorFlow or Keras, but in this case, still leverage the same REST interface for deployment. We added the Italian language for cognitive text analytics, like extracting topics and keywords, and text summary and similarity. This adds to the already supported English, Spanish, and French. For convenience, we've simplified the URL structure and introduced additional model metadata filters when retrieving models. But let's move on to the OML roadmap. On the right of our timeline is a high-level summary of the range of enhancements we have planned through 2023. Let's jump into a few of these. OML monitoring expands support for the data and model lifecycle. There are many aspects to monitoring. Here are a few initial areas we'll be addressing: data drift detection, model drift detection, and bias and fairness monitoring. Data drift involves identifying when the statistical properties, like distinct values or mean and variance, significantly change. Model drift involves identifying when the user-specified model metric, like accuracy or R-squared, significantly changes, or perhaps the distribution of predicted values deviates too much. Bias and fairness are important to help ensure against putting certain groups or individuals at a disadvantage. This can occur, for example, if the data where certain groups are excluded or underrepresented, or in models where distinct populations may be combined inappropriately with outcome probabilities that are adversely affected. Well, let's illustrate data and model drift detection for a moment. Data drift may indicate the need to rebuild a model. Essentially, we start with some baseline data and compute an initial drift metric. Later, we evaluate new data to see if the computed metric surpasses our alert threshold. When new data deviates sufficiently, an alert is recorded. And this informs the user that rebuilding the model is likely needed. Similarly, model drift includes observing if the model metric is degrading over time, again suggesting that rebuilding the model may be warranted along with possibly investigating root causes. Like data monitoring, users provide new test data sets periodically to evaluate the model metric. Some scenarios may include building multiple models, using, for example, different algorithms or settings, and these models then compete based on their accuracy metric. This champion score can guide which model should be used by an application. When the metric goes below a defined alert threshold, this fact is recorded so the user can decide if the model should be rebuilt. Later this year, with OML services, we're adding support for batch scoring for in-database models and then ONNX format models. This allows using the same REST API as you would now for singleton and small batch scoring, but doing this at scale in the database. In support of these longer running jobs, OML services will also support asynchronous invocation to avoid blocking the client process while scoring occurs. As we introduced earlier, the AutoML UI provides a simple interface for defining experiments that leverage automated machine learning for structured data. However, many use cases can involve unstructured text as well. Consider doctor notes that accompany patient records, or call center rep notes on a customer. To enable users to benefit from the integrated text mining capabilities of the in-database algorithms, we'll be allowing AutoML to accept unstructured text columns as input. Here, tokens are automatically extracted for use with other structured data to enhance model accuracy. The next enhancement is experiment scheduling. OML Notebook supports defining jobs to schedule notebook execution. Experiment scheduling for the AutoML UI facilitates greater automated deployment using that same jobs interface. And to further improve performance and scalability, the AutoML pipeline will further optimize algorithm settings to support classification targets where there are many possible values, such as when recommending multiple products. We also continue to add new machine learning techniques, in this case to support use cases like demand, sales, and inventory forecasting. For this, the AutoML UI will support time series using in-database exponential smoothing. Also later this year, we'll add support for third-party Python and R packages installed through the creation of Conda environments. This much requested feature allows adding open source packages for use with the Python and R interpreters in notebooks, as well as for use with embedded R and Python execution. On the roadmap for OML for Pi is support for datetime and integer data types, also much requested features. Later, we'll be adding the ability to reproduce the full AutoML UI pipeline programmatically. OML for Pi will also enable programmatically deploying in-database models and exporting ONNX format models directly to OML services. This provides a seamless way for Python users to hand off their models to other members of the data science team. Slated for Oracle Database 23c, we have multiple enhancements. Let's touch on a few of these. First up, the classification and regression in-database algorithm XGBoost will support a new machine learning technique, survival analysis. You might know that survival analysis can be used to predict churning customers and employees, as well as estimate equipment lifetime. And in critical situations, survival analysis is important when the time between exposure and event is of critical interest, such as 5-year survival among patients with tumors. We have improved data preparation for high cardinality categorical features, which addresses poorly prepared data, so it not only can increase model accuracy, but also reduce memory and compute demands when building models and scoring data, which further enhances scalability. And in support of the machine learning lifecycle, we'll introduce greater lineage metadata for both data and models to enable tracking relationships between input data, models, and their dependent model details. In-database algorithms will take advantage of the new database column limit of 4,000. The column limit increase makes it much easier for users to work with wider datasets in standard form. You may recall that in-database models already allow even tens of thousands of columns using nested tables. But this new column limit makes it more accessible for typical data representations and database users. We're introducing automated model search for time series models, where hyperparameters are automatically selected. Since there are many such settings, this not only can be a major productivity tool for data scientists, but also enabler for non-expert users. But let's take a look at the last item, time series regression, in more detail. Time series regression supports one or more time series, along with flag variables like holidays or events. This extends OML's existing time series exponential smoothing algorithm. At one level, the predictor time series values are first forecast and then used with the flag columns to build a multivariate regression model. You'll also find OML in and on the roadmap of other Oracle products. For example, OCI Data Catalog includes in-database model metadata. On the roadmap is the addition of metadata from OML services. OCI Data Science will be including the OML for Pi client in their database Conda environment. Users can also export supported models in ONNX format and import them into OML services. Oracle Analytics Cloud already makes it easy to work with in-database models directly from OAC, but will be integrating in-database AutoML support from OML for Pi. We're also collaborating with the Oracle Data Integrator team on future store functionality. This includes, let me go back. We're also collaborating with the Oracle Data Integrator team on feature store functionality. This includes feature management and engineering. I'm going to try that again. We're also collaborating with the Oracle Data Integrator team on feature store functionality. This includes feature management and engineering. ODI also supports visual construction of data pipelines through a no-code user interface for performing transformations and scoring with in-database models. This illustrates some of the feature store-related functionality in ODI. Here we see data flow details, where we're performing a data transformation. We can save this as a new data entity in the feature store with tags for easily finding useful data and listing data entities to choose from. Coming back to Oracle Analytics Cloud, this will enable a single-click AutoML engine within OAC, so users can benefit from OML for Pi AutoML seamlessly, never having to leave the OAC environment. This makes ML easy and efficient for non-expert users. Oracle applications teams have also augmented their products with Oracle Machine Learning. They cite multiple advantages of using OML, including in-database model building and scoring, scaling to enterprise data volumes, ease of development, integration, and deployment, SQL, R, and Python APIs, and environments with no-code interfaces, and of course, database-level security, just to name a few. Here are a few OML customers. DX Marketing delivers better analytics with machine learning, delivering projects 70% faster with significant revenue growth. The UK NHS achieved major savings using in-database algorithms for fraud detection. Forth Corporation in Thailand maximizes their marketing resources, achieving a 2 to 3 times increase in conversion rates. And Sensa Analytics uses in-database machine learning to reduce payment processing time from months to a couple of weeks, processing thousands of claims daily. For more information on Oracle Machine Learning and to get started using OML, check out these resources. In addition to our webpage and blog, our GitHub repository contains code examples and notebooks using the various OML APIs. Our office hours provides updates on OML technology, how-tos and use cases, and product demonstrations. To try OML Autonomous Database, check out Oracle Live Labs. For example, the link here is for OML Fundamentals, which covers several of the components we've discussed. Thanks for joining me to learn about Oracle Machine Learning. Enjoy the rest of the conference.